Okay. Hello, everybody. So welcome to Extreme Universe online colloquium, funded by Mixed Kakenhi Grant in Aid for Transformative Research Areas A. This new collaboration program called Extreme Universe was just started in last September. And I'm Tadashi Takayagi. I'm head investigator of this program. And in this Extreme Universe collaboration, we would like to understand fundamental problems in physics, such as quantum black holes, quantum cosmology, and dynamics of quantum matter by considering quantum information as a fundamental component of the natural world. This colloquium is one of the main open activities in this program to provide an interdisciplinary opportunity for researchers working in quantum information theory and also physics. Today, as the first colloquium speaker, we are very happy to introduce Professor Shinsei Ryu from Princeton University. He also kindly agreed to be one of the members of this advisory committee. Shinsei got his PhD in University of Tokyo in 2005, and after that, he became a postdoc at KITP at Santa Barbara. And when I enjoyed a wonderful collaboration with Shinsei, and at the time, I was quite surprised that Shinsei was already very much familiar with string theory, even though he's a condensed matter theorist. In 2008, Shinsei became a postdoc fellow in UC Berkeley, and 2011, he became assistant professor in University of Illinois, Urbana-Champaign. And in 2017, he joined in University of Chicago as associate professor. And in 2020, he became a professor in Princeton University, and until now. And Shinsei, as you know, Shinsei is very famous for many outstanding contributions to condensed matter theory and its connection to high energy theory, and such as discovery of periodic table of topological initiators and analysis of quantum entanglement in quantum manifold systems and field theory and holography. And indeed, he has been awarded various outstanding prizes, which includes Simon's Investigator Award, Nishina Memorial Prize, New Horizon in Physics Prize, Nishinomiya Yukawa Memorial Prize, and Condensed Matter Science Prize. So, okay, so let us now start with today's colloquium. So, Shinsei, please share your slide. Yes.
Okay, so is it
sorry, just okay. So Shinsei Ryu will talk about many-body quantum physics through the lens of quantum entanglement. Please start.
Thank you, Tadashi, for the kind invitation and the introduction. I hope you can all hear me. And then, yeah, thank you for coming. I think it's Saturday in Japan, I think. But thank you for coming. So today I want to talk about aspect of many-body physics, basically quantum aspect of many-body physics. And then I will use the concept from quantum information theory, basically quantum entanglement, to understand various many-body phenomena in quantum physics. So the my target today is then many-body quantum systems. And then I think many of you may be working on various kinds of many-body quantum systems. Since I'm a quantum condensed matter physicist, for me, quantum many-body Hamiltonian may be looking like this, or in some other cases, it may be looking something more like a quantum spin systems. Or some of you may be working on the high energy physics, then you may be interested in studying a quantum many-body system, which may be looking like this. In all these cases, the common feature is that we have a large number of degrees of freedom. And then that is a source of a very rich phenomena which may occur in these quantum many-body systems. Just to name a few examples, these systems can exhibit spontaneous symmetry breaking, or maybe it can exhibit something called topological phases of matter. That is one of the central themes today. Or they can exhibit many non-equilibrium, many interesting non-equilibrium physics as well. So today we want to discuss at least some of these physics in many-body quantum physics. Unfortunately, many-body quantum systems are known to be very difficult to solve, at least by using classical computers. It's simply, at least naively, the dimension of the Hilbert space is exponential in terms of the degrees of freedom. So it becomes quickly very difficult to solve many-body quantum systems by using classical computers. On the other hand, this quantum aspect is also source of very rich phenomena. So in particular, we could have a kind of correlations or quantum correlations which do not exist in, let's say, classical systems. And then that is already known in the context of few-body quantum systems, let's say systems with two spins or two qubits. And then we could have something like a Bell pair or EPR pair, which has very interesting correlation, which Einstein called the spooky action. So we want to explore quantum correlations, quantum physics that can happen in quantum many-body systems. Okay, so that is the I think one of the main theme or main driving force in the modern condensed matter physics. So we want to explore the consequence of quantum mechanics in many-body settings. But on the other hand, the quantum many-body wave function, in particular when the number of degrees of freedom is very large, the pattern of quantum entanglement is very complicated. So we are still trying to understand various kinds of quantum many-body correlations in our favorite quantum many-body systems. Okay, so in few-body systems, for example, in two-body systems, it is relatively maybe not super easy, but it's relatively well understood that we, for example, for the system 2 qubits, we can distinguish these two kinds of states, product state and the entangled state. And we can make a similar distinction for many-body wave functions. Once again, it's not super easy, but at least we can expect to have a distinction between non-entangled state and the state with a lot of quantum entanglement. For example, we could have a state where we have a product of this product form. And then, for example, for spin systems, we could have a wave function where all these spins are pointing in the same direction. So that could be the simple wave function that can describe a magnetism, for example. On the other hand, yeah, so this type of wave function or this type of order is ubiquitous in many condensed matter systems. We are going to say a little bit more about this in a minute. On the other hand, quantum many-body systems can exhibit a much more interesting kind of wave functions. For example, back in 70s already, Anderson kind of envisions a very entangled quantum many-body wave functions. For his motivation, he wanted to understand a frustrated magnet, quantum magnet, and later he also wanted to apply this type of wave function to the physics of a high-TC superconductor. So what he proposed, what he envisioned was this type of wave function where, so this is supposed to be the wave function for some quantum spin system where these spins are forming a Bell pairs. So each these blue circles represent the bell pair, and then many body spins are forming a bell pairs, but they are kind of switching partners. So we have a superposition of many various kinds of pattern of bell pairs. So this is something he called the resonating valence bond state. Okay. So this in the modern language, this is the example of spin liquid. I'm going to say a little more about this, and then in particular, there's a particular spin liquid which is also a topologically ordered. Okay. So this prototypical example between unentangled state and the entangled state. This contrast also shows up in many body quantum physics, in particular in modern condensed matter physics. Okay, so now I want to say a few more words about this conventional versus a topological order in many body quantum systems. Okay, so yeah, in fact, this is the first kind of wave function, which is a bit boring from my point of view. Although they are boring, they appear in many condensed matter systems. So many phases, in fact, they are characterized by this type of product wave function. And then they are characterized by some sort of a order parameter. For the example I just showed you, it can be just the total magnetization. In other examples, we could have something like something slightly more complicated than magnet. We could have a something like a superconductivity. But anyway, in these cases, we have a or maybe superfluid. Maybe it's a for my purpose. Maybe superfluid is a better example. But in these cases, we can sort of identify some form of order parameter, sometimes a local order parameter. And then by using a local order parameter, we can distinguish different kinds of phases in many body systems. And it is well known since Landau and Gensburg, and then perhaps Wilson, we can describe different phases and perhaps even the phase transitions between these phases by using Gensburg-Landau type theories. Okay, so we have this free energy landscape which changes as we change parameters of the system. Okay. Oh, by the way, I don't know the format of this colloquium, but if you have a question, maybe I don't know, maybe you can just unmute, or you can just ask later, or maybe I'm not sure if I should.
Okay. Maybe could you also accept the question in the middle?
It's up to you, but I can accept the questions. Yeah. And then
thank you very much.
Monitor chat window or something like that. Or maybe there's no chat window. So maybe yes.
There is also chat. There's also chat window here.
But there's also chat window. So yeah,
or
maybe
we can raise or hand. We can raise hand. Also maybe just speak up in cases.
Okay. Okay. Either way, please feel free to interrupt. Okay, if you have questions. Okay. So anyway, this is a conventional paradigm which has been used for a very long time in quantum many body physics. But on the other hand, I think something like around 1980s or later, people gradually started to realize that there are more peculiar kinds of quantum many body systems which may escape this type of a symmetry breaking paradigm. So the example of such a peculiar systems or peculiar phases are topological phases of matter. So simply put, these are the systems which escape from the symmetry breaking paradigm. So there's no convenient order parameter to describe them. Instead, we need somewhat more sophisticated or subtle characterization is necessary. For example, the good example is the quantum Hall effect. where we need a topological invariant to distinguish different phases that occurs in the quantum Hall system. So here in this particular case, we can distinguish different phases or different plateaus that occur in the quantum Hall effect by using the quantized Hall conductance, which is the topological invariant. And in more recent years, people discovered a lot of other topological phases of matter, such as the topological insulators, topological superconductors. And then in spin systems, we could have something like Haldane spin chain and so on and so forth. There was a Nobel Prize for these systems in 2016. And then, so perhaps you may have heard about these systems. Today, I'm going to mainly talk about topologically ordered systems. So that can be thought of as an example of topological phases of matter. But in addition to these things I just said, they have more interesting properties. So I'm going to talk about topologically ordered phases in 2+1 dimensions. So these are phases which are characterized by their peculiar elementary excitations. So these are phases that support excitations called anyons. And the anyons are very peculiar excitations, which are neither bosons nor fermions. Instead, they have a non-trivial exchange of braiding statistics. So if you have two anyons, then you can exchange their spatial locations. And then for fermions or bosons, your wave function picks up either -1 or +1. But for anyons, you can get something else. For example, you could get a phase factor, which is neither 0 or pi. And then even more exotic case, you can get a totally different state. Even if your particles go back to their original position, your wave function may not go back to itself, okay? So that is called non-Abelian topological order. For Abelian topological order, up to this phase factor, your wave function may go back to the original wave function. If this phase is not a 0 or pi, that is already strange. There's also even more strange one, which is this non-Abelian topological order, okay? Anyway, topological phases or topologically ordered phases are peculiar phases which support anyons. And then once again, these phases are not characterized by a symmetry breaking nor order parameter, but instead they have to be characterized by the properties of these anyons, okay? Just to quickly summarize the known properties of topological ordered phases, I just here make some quick table. So for the conventional phases, which may exhibit a spontaneous symmetry breaking, we could have a elementary excitation such as a Nambu-Goldstone bosons, in particular when the symmetry in question is continuous. And then they can be described by Landau-Ginzburg theory, but instead in topologically ordered phases, we have a elementary excitations which are not boson nor fermions, but we have anyons, and we have some other framework than Landau-Ginzburg theory. In this case, this framework is called topological fissure theory that describes the properties of anyons. Okay. One more interesting feature of a topologically ordered phase is the bulk boundary correspondence, which I may come back later. Okay, so this is rather formal introduction to topologically ordered phases, but these phases have been realized, or we believe we have a realization of these phases in various systems. So the most famous setting is the fractional quantum Hall effect. So previously I showed you a quantum Hall effect, but that was an integer quantum Hall effect. So we have a transport or Hall resistance, which has a plateaus at integer values. But for the case of fractional quantum Hall effect, we have a quantization of the Hall conductance at some fractional numbers. Okay, so that is the famous setting where we could have a topologically ordered phases. They're having also active search of spin liquid, topological spin liquid, which can be realized in let's say spin systems. And then more recently, people started to realize topologically ordered phases in the quantum simulators. Okay, so for example, this is the array of Rydberg atoms. They are aligned on this fashion on the Kagame lattice, and then quite recently people started people started to engineer such systems. So we believe, okay, maybe not all of us, but people are thinking that this type of Rydberg systems may realize a quantum spin liquid wave function. Okay, so this is, I think it's actual optical image. This is the kind of schematic wave function, like the wave function I showed you before for the resonating valence non-solid. So then I think that there is a challenge for topologically ordered phases since there's no local order parameter. So the conventional phases with spontaneous symmetry breaking, we can detect them by using a local correlation functions. But since topological order, they escape symmetry breaking paradigm, there's a question of detection. So detecting topological order is much more difficult than detecting conventional order. There's some recent result, which is perhaps, like last year, which was almost like a first experimental evidence for at least abelian topological order, but it is quite recent. So detecting topological order in experiment has been very difficult. Okay, and then these experiments, they use transport experiments so they use the some sort of transport probe to try to detect a abelian topological order. But in this talk, I want to use the something which is closely related to entanglement to detect topological order. One motivation for looking for experimental probe related to entanglement is that this type of transport experiment is maybe quite common in solid state systems. But once we start to realize a quantum many body systems in quantum simulators or designer quantum systems, such as the Rydberg atoms, cold atoms, and the other systems, maybe systems of qubits, then these conventional probes may not be easily available. So, but instead, we may be able to detect a topological order in such a quantum simulators by directly measuring quantum entanglement. Okay, so then I will try to introduce some way of detecting topological order by using the concept of quantum entanglement. So we have let's say we have some quantum systems realized on the two-dimensional plane, okay? Then we can discuss a quantum entanglement by computing the entanglement entropy. So we bipartition the total system into two regions, A and B. And then we could trace out one of these two regions. Let's say I trace out all degrees of freedom in this region B. Then I can get the reduced density matrix supported on region A. Okay. then we can compute or we can define the entanglement entropy from this reduced density matrix. Okay, so this quantity, entanglement entropy, has been discussed in many different many-body quantum systems. In the context of topologically ordered systems, Levin-Wen and Kitev and Preskel, they did the seminal work where they showed that entanglement entropy obeys this scaling law. So in topologically ordered phases, entanglement entropy has this area law part where L is the typical length scale associated to this region A. So this part is proportional to the area of region A. But what these people discovered was that there's the additional term which comes with the minus of some positive number. It is written as log D. And then this part of the entanglement entropy turns out to be a universal, which is not affected by the microscopic details. And also it is closely related to the universal data which characterize the topological order. Okay, this term is known as the topological entanglement entropy. Okay, so by looking at this scaling relation from the entanglement entropy, we can detect the topological order from the entanglement. Okay, so that was the well-known work by Levin-Wen and Kitev and Preskel. So what this says is that basically there's the area law contribution to the entanglement entropy that is basically reduced by this term. This term is coming from the long-range quantum correlation or long-range entanglement of the topologically ordered ground state. Okay, yeah. We can also look at the spectrum of reduced density matrix. So this is a sum of, this is basically a sum of eigenvalues of the reduced density matrix. But we can also just look at the spectrum of reduced density matrix that is known as entanglement spectrum. And it is also known to detect various topological aspects of the topological phases. So for example, it is known that rho A behaves as the exponential is given by the exponential of HH, where HH is essentially the physical Hamiltonian that describes the boundary excitation or edge excitation of topologically ordered phases. So this can be thought of as a realization of bulk boundary correspondence, which I briefly mentioned earlier. For non-interacting system, I made a plot here where I have a physical, here in the spectrum, I have a physical boundary excitation, its excitations. But if you look at the spectrum of density, reduced density matrix, you also see the boundary mode or edge mode in this spectrum. Okay. So that is useful. I think I'm a bit slow in time, so I may almost skip this part. But I also want to say entanglement entropy is useful not just for topologically ordered phases, but it is also useful to discuss various other aspects of a quantum many-body system, such as the dynamics in quantum many-body systems. So we can discuss the entanglement time evolution of entanglement entropy in some dynamical process, no-equilibrium process, and then the entanglement entropy growth, for example, can be used to distinguish various kinds of quantum dynamics, such as ergodic dynamics or non-ergodic dynamics, including many-body localization. So I can just want to show you some example. I want to show you this example because basically I want to say that quantum entanglement can be measured experiments. So it wasn't possible until very recently, but finally people found a way to realize the experimental measurement of entanglement entropy in the synthetic quantum simulator systems. So here entanglement entropy is here. It's measured in the cold atomic systems, which is showing many body localization. So entanglement entropy growth is very slow. This is logarithmic in time, and that is the evidence of many body localization. Here, this is slightly different protocol where people utilize the randomized measurements to measure the entanglement entropy, once again, in cold atomic systems. Anyway, so entanglement entropy is becoming experimentally accessible. I think it's still rather difficult to measure, but in the future, we can be hopeful that they can be more accessible, and then perhaps we can use these quantum information theoretic quantities to study various aspects of quantum many-body systems. Okay. So yeah, so I think I may be spending too much time on introduction, but today I want to once again study topologically ordered phases by using the Prof from quantum information theory. And then I want to go beyond basically a topological entanglement entropy or entanglement entropy. So in this talk, I'm going to study something called the entanglement negativity and also reflected entropy. I will tell you what these quantities are, and then I will present our recent work where we computed these quantities for topologically ordered systems. Okay, so now I'm transitioning to the next section, and I think there's perhaps so far no question. Okay, so once again, the framework I presented so far is limited in the sense that we so far consider a bipartitioning of the system. So we have a system, let's say on the two-dimensional plane. I bipartitioned my system into region A and B. So there are two regions. But one could say why we stop there. So we can go beyond bipartition, and then we can start considering a tripartition, like we partition the two-dimensional system into 3 regions or even more regions. But for my talk, I limit myself to a tripartition. So now I have a 3 regions, A, B, C here. Well, if I have a torus, for example, I could tripartition my torus in this way. Then we can discuss a more subtle quantum correlations by using a entanglement quantity other than entanglement entropy. Even for few qubit system, so I started with the example where I only have 2 qubit, but if I have a 3 qubit, it can exhibit a more interesting entanglement pattern, such as a ZHZ state or W state. So we could ask similar questions in many-body context. So if we start to tripartition my many-body wave functions, we can ask what is the pattern of entanglement there, okay? Then I will mainly focus on these 2 quantities to study entanglement properties of many-body wave functions. Okay, so I hope the motivation is clear. So what are these quantities? So I will first introduce entanglement negativity. So entanglement negativity is closely related to the following question. So if I have a mixed quantum state for the composite quantum system, A union B, how do we quantify the quantum entanglement in the mixed states, which is described by this density matrix rho A union B, okay? So previously we discussed the entanglement entropy, which is a perfect entanglement measure at 0 temperature. If I have a pure quantum state, basically entanglement entropy is a very good entanglement measure. But that is not the case if I have a mixed quantum state. If I have a mixed quantum state, entanglement entropy basically capture not just the quantum correlation, but also classical correlations. So if we are only interested in entanglement properties, entanglement entropy is not a good quantity. Slightly more technical level, entanglement entropy is monotonically decreasing under this operation called local operation, the classical communication, which is not the desired property to quantify entanglement measure. Instead, we can consider something called entanglement negativity or logarithmic negativity, which is defined here. This quantity is supposed to be a better quantity than entanglement entropy for when we are discussing mixed quantum state. Okay, so first of all, it is a good entanglement measure in the sense that it does monotonically increase under local operation and the classical correlation. So that's what we expect for the quantum entanglement. So we should not increase quantum correlations just by local operations. So that is a desired property. So then the way it is defined is to make use of the concept of partial transpose. Okay, so so I think to describe what entanglement negativity is, I first need to describe the operation partial transpose. So that is in the next slide. So it's a very simple operation where if I have a composite system HA tensor HB, I write out the matrix element for some operator M. The partial transpose operator M with respect to subsystem B is just take a transpose only for subsystem B. So I exchange indices here without touching the index for associated to this subsystem A. So that defines this partial transpose. So just like we use partial trace to describe to define entanglement entropy, we use partial transpose to define entanglement negativity. So once you take a partial transpose, then you look at the eigenvalues of the partially transposed density matrix, and then we look for a negative eigenvalues. So that's why this is called entanglement negativity. Okay. And then we basically sum over all negative eigenvalues that appear because of the partial transpose, and we just put some weight, which is this absolute value of the eigenvalue itself. So the basic intuition is that if your density matrix has no correlation between A and B, it may be looking like something like a diagonal matrix. Then taking the transpose that touches the off-diagonal part of the density matrix, they are not going to be affected by partial transpose. On the other hand, if we have a complicated density matrix with a quantum correlation, we expect that they are going to be very much affected by partial transpose. And in particular, a spectrum of density matrix will be dramatically changed by partial transpose. And then it may appear, these negative eigenvalues may appear. Okay, so that is the kind of quantifying how much that density matrix is affected by this partial transpose. So this can be used as the measure for the quantum correlation between A and B. Okay, it is often convenient to take a log of this quantity to define logarithmic negativity. And then I think for the rest of my talk, I will just call this log negativity as a negativity. So I'll be talking about this quantity calligraphic E. Okay, so that's the entanglement negativity. I will be actually discussing fermionic systems where this definition of partial transpose is not enough. So to define partial transpose for fermionic systems, it is actually not so straightforward as this. I have a kind of series of publications which try to clarify this point. It's a bit technical, so I do not go into details here. But I just want to say that for systems, like fermionic systems or maybe systems of anyons where we have a intricate particle statistics to define partial transpose, we have to take into account the statistics properly. But some technicality I'm going to skip. But we are going to use the properly defined partial transpose to discuss entanglement negativity. Okay. Next quantity I want to discuss is this reflected entropy. So that's the that is defined in the following way. So I first have a density matrix rho defined for these two regions A and B. To define reflected entropy, I first double the degrees of freedom. So I have a copies of this system A and B, region A and B here. They are denoted by A star and B star. And then you can write down a now pure state for this extended system, which is written here. And this state is designed such that once you take a trace over these copies, A star and B star, you get this original state rho AB. So this is called canonical purification. And then the well-known example is a Summerfield double state. Okay. Now to define reflected entropy, instead of tracing out A star and B star, I trace out B and B star. Okay, this region. Then I'm left with the density matrix defined on this region A union A star. And then we can compute the von Neumann entropy for that density matrix. Okay, so that defines this reflected entropy, which I'm gonna call RAB. Okay, so this is the kind of correlation measure that has been proposed fairly recently by Data and Faulkner. And their motivation was to study, to make use of this quantity to say something about a holographic duality, ADS-CFT, for example. That part is not so much important for me today, but we just use this as a good quantity to study topological ordered phases. Okay, right. So so with these definitions, I now want to discuss how we make use of these quantities to study topologically ordered phases. Okay. So yeah, we go back to this picture. So I am interested in a tripartitioning, let's say, topologically ordered phases, okay, defined on a torus or a sphere or maybe plane. And then we are going to compute these entanglement quantities such as negativity and then reflected entropy. So yeah, we are interested in yeah, like what can we learn by studying these entanglement quantities? So that is the main theme of this talk. We already discussed the topological entanglement entropy, and then there's this part which is written as log D or minus log D. That is a one universal number, but it does not capture all the universal aspects of topological phases. So like I said earlier, topological phases must be characterized by properties of anyons, which is not just one number. We must know statistics between all kinds of anyons and then other data as well. So to capture something which was not captured by topological entanglement entropy, we are interested in studying these quantities which may tell us something more about topological ordered phases. Okay, so the calculations I'm going to show you are presented here. So one is the slightly older work done in 2016. I present these results as a kind of warm-up. And then I will move on to more recent result, which appeared like a few months ago. That is about this setup. So yeah, the first paper is about this setup on the torus. And the second paper is about this way of partitioning a topological phases. Okay, so I will start with this setup on the left-hand side. Okay, so I'm going to study topological phases or topologically ordered ground state defined on the torus. Okay, because of the presence of anyons, as it turns out, there are a degenerate ground state on the torus. Okay, that is one of the defining properties of the topologically ordered systems. That is basically a consequence of the presence of anyons, as it turns out. So I'm going to consider some state which is a linear superposition of degenerate ground state. So this HA is some sort of basis in this degenerate ground state. So the technical aspect is that these states are characterized by the presence of a anyon loop or Wilson loop, which is running in this direction. Anyway, it's it's one of the topologically ordered ground state, and I consider some linear superposition. And then we go ahead and compute the entanglement entropy. There's interesting technical details, which I'm going to say something a little bit about later. But for now, I just want to show you a result we got. So this is the entanglement negativity, which I get. So we first consider a tripartition. So we partition a torus into 3 spatial regions, A1, A2, and B. Okay, then I trace over B. So I start from the pure state on this torus, but I trace over region B. Since I trace over region B, I get the mixed quantum state defined on this region A1 tensor A2. Since this is a mixed state, it is useful to study, to use negativity to study this mixed state. So I take the partial transpose, let's say for region A2, then we compute entanglement negativity. Okay. To contrast the negativity, just for the comparison, I also presented something called mutual information. But let me start with entanglement negativity. The first part just depends on the area of this region A2. So this is the area law term, just like an entanglement entropy. Second part is once again minus log D. So this part has the same information as entanglement negativity. So topological entanglement entropy. Now, new information that negativity capture is basically this third term, which depends on the linear superposition psi A. And also this small dA is the something called quantum dimension that is associated to each topological ground state. Okay. Interesting aspect of this result is that if your quantum system, your topological system has a abelian topological order. In that case, this number dA turns to be all 1. The third term is completely gone. Okay, but if you have a non-abelian topological order, third term is there. So then we have a dependence on the particular linear superposition we are taking. So it seems from this calculation that entanglement negativity can tell us something about abelian versus non-abelian topological order. Okay, so which cannot be. Yeah.
So this log dA seems to be goes to 0 if dA equal 1. So
right.
Looks like divergent.
Oh right. Yeah, maybe I'm saying something strange here. Yeah, maybe there's no log here. Okay, sorry. So yeah, that's
maybe no log. I see.
Right. Yeah, that's absolutely right. So yeah, there may be something wrong about this, but this must be still true that if dA is all 1, basically this term is gone. Yeah. Yeah. Thank you for the question.
sorry, here I have a question. So negativity is related to entanglement, and mutual information is related to entanglement, and also classical correlation.
Right.
And do you see some such a qualitative difference between these two?
Yeah, so at this stage, I don't know how to distinguish classical versus quantum correlation. Maybe we need to subtract or something like that. But yeah.
I see. Yes. Coefficients seem to be different between these two.
Right, coefficient seems to be different, right? So yeah, that may reflect this classical versus quantum correlation, but I don't know how to clearly distinguish them. Okay. Yeah, so this is one older result which I want to use as a warm up, and I think I'm already running out of time, so I should speed up a little bit. So now I move on to this more recent result where, so say I'm using sphere to represent my setup. So I have a topological phase on the sphere, but I tripartition this sphere into 3 regions, and then I discuss the entanglement negativity and the reflected entropy. Okay, I took a particular example, which is chiral P-wave superconductor, and then integer quantum Hall effect. Okay. They are characterized by this number central charge 1/2 and 1, and they're going to be important later. Okay, and once again, there's an interesting technical kind of details, but I first skip technical details and just show you some result. Okay, so first we look at the spectrum of partially transposed density matrix. That is called a negativity spectrum. So just like an entanglement spectrum, we can look at the spectrum of partially transposed reduced density matrix. That may tell us something about the property of topological reordered phases. So then this is the result we got. And then these eigenvalues are complex in general, and it is non-trivially distributed over complex plane. We also see a kind of 2 or 3 kinds of branches here. One branch, I have this circular branch, and there is also this middle branches, which are centered around the real axis here, okay? So I will later show you some numerical data where we study this spectrum for topologically trivial phase. In topologically trivial phase, we have a eigenvalues just clustered around 0 and 1, and we don't see this non-trivial distribution. So this non-trivial distribution seems to be the fingerprint of topological order. Okay, we have been studying this negativity spectrum, in fact, not just for topologically ordered phases, but we studied this quantity for 1+1D critical systems, conformal field theory, and also a 1+1D topological phases, topological superconductor. In all cases, we have a non-trivial distribution of these eigenvalues. For example, here, this is the negativity spectrum for conformal field theory in 1+1 dimensions. We have this six-fold structure here, okay? So it's, once again, eigenvalues are non-trivially distributed, okay? So that's the first thing I want to show you. The next thing I want to show you is this reflected entropy. So here we take this particular combination, reflected entropy minus mutual information, and then this is the calculation by changing some sort of cutoff, but it is constant. This plot here is consistent with this behavior, where this difference, which is sometimes called Markov gap, is given by C/3 times log 2, which is this universal number. And then here C, once again, is the something called central charge, and it's 1/2 for the chiral P-wave superconductor, and it's 1 for the integer quantum Hall effect. Okay, this agrees with the recent claim made in this paper. Okay, so this number here, central charge, is the kind of universal data once again, which characterizes the topological phases. And then chiral version of the central charge can be measured in the thermal transport. So once again, this is fairly recent experiment where people finally started to measure this chiral central charge in topologically ordered systems such as the quantum Hall systems and some sort of spin liquid. But as it seems, this Markov gap seems to capture this central charge. So yeah, this is the kind of entanglement quantity which can extract central charge. Okay, there's another recent paper by Kim, Shi, Kato, and Albert, where they also have some formula, once again using a quantum entanglement quantity that can give us this chiral central charge. Okay. Strictly speaking, the central charge we are getting here seems to be more related to the total central charge. Although in my calculation, I only have a chiral phase, so it's there's no distinction between total and chiral central charge. But anyway, modulo that details, this is the interesting quantity which can, first, it is universal, remarkably universal, and this seems like it captures this central charge. Okay. Right, so finally, I want to say a few words about the calculation itself. So we computed these quantities by utilizing bulk boundary correspondence. And then it is, to our surprise, it seems like it is related to a string field theory. So what is string field theory? It's a many-body theory or many-body framework for string theory, or second quantized version of string theory. So this is just to quickly show you technical highlights. So in string field theory, we have a vertices, interaction vertices that describe the interactions between different strings. Here we have two strings interacting with each other, they connect, and then as time elapses, we may get one string. Or if time goes this way, I start with one string that can split into two strings. Okay, that is the way we describe interaction vertices in string theory. To make a connection to what we care, we first deform this diagram into this way, and then I take this direction as a time. So this diagram now gives a creation of three strings out of nothing. Then we get some sort of interacting state for three strings. So this state is defined in the Hilbert space of three strings, and this state I'm calling B, or vertex state. Okay. We basically found out that this vertex state is approximate the topological ground state of our interest near the entangling boundary. Okay, so here I kind of drew my sphere by deforming this sphere such that I elongate this region A, B, C to have a three infinite cylinders, semi-infinite cylinders meeting at this junction point, so they are connected. And then we can find so then in this geometry, near the entangling boundary, I have a three edge series interacting with each other. So then our claim is that this topological ground state near this junction region is essentially given by this vertex state, which we learned from this string field theory context. There's a similar technique which allows us to compute a topological entanglement entropy, just for the case of bipartition. But as it seems, this string field theory technique naturally allows us to generalize this approach to multi-partitioning of topological phases. So this is one quick technical highlight. So perhaps I have to skip this, but we also check our result by using particular lattice models. So we get a result consistent with our continuum field theory calculation. this Markov gap is also consistent with what we got. And then here's a summary and outlook. So we studied this multi-partitioning setup and then studied entanglement quantity other than entanglement entropy. And then we capture topological aspect or topological data, which was not captured by topological entanglement entropy, such as a non-abelian nature of topological phase or total center charge. And then, technique-wise, we use string field theory. So we are also wondering if our calculation has some implication in string field theory, maybe. And then it may be also interesting to study other quantities. So we still don't have a complete picture, like what kind of entanglement quantities tell us which part of the topological data of anion. So we are pretty much still exploring this program to detect all topological data by using entanglement-related quantities. So I think with that, I want to stop. So thank you for your attention.
Thank you very much for a very beautiful colloquium. So starting from history of topological order and lots of very interesting recent updates. So, okay, so it's time for questions. Please ask questions. So just to speak up if you have a question. Otta-san, do you have a question?
Can I have a question? I have a question about the string field theory part. So could you explain again the slide, for example, by using quantum Hall system like that? So you said some Banach boundary correspondence. So it is related, it should be related to the quantum Hall system like that. So could you explain more explicitly or in detail about that?
So I'm happy to explain. I don't know how much details I can convey here, but once again, okay. So I start with this geometry. So I have a sphere, but I'm interested in having entangling boundaries here.
Mm-hmm.
But I kind of just redrew it here. So I have such that I need to know the ground state near these entangling boundaries, because that's what it matters when we try to compute reduced density matrices. By bulk boundary correspondence, the relevant degrees of freedom around this entangling boundaries are expected to be the edge degrees of freedom.
Mm-hmm.
Okay, I have a 3 regions, so I have a 3 copies of H series. H series on the boundary of region A, on the boundary of region C, on the boundary of region C.
Mm-hmm.
But they interact at these entangling surfaces, just like these 3 strings interact. Okay,
Mm-hmm.
So this is just an analogy I'm making, but as it turns out, the way these edge state interact is precisely these strings interact by this diagram.
So in this case, the string propagate in 1 plus 2 dimensional space time, right?
Exactly. So that is actually an interesting point. So this picture looks like, this vertex, but here I'm drawing, in fact, 2 plus 1D, two-dimensional surface.
Okay.
Spatial surface. Here, this is actually 1 plus 1 dimensional space-time surface.
Mm-hmm.
So there's a difference here, but as it turns out, they are pretty much related.
So you show something in the quantity levels using this string field theory.
Yeah, so we didn't prove it, but we basically kind of convinced ourselves that this is a very good approximation.
Okay, thank you very much.
Okay.
Any other question? So let me ask a question about related to this Hotta-san question. So this is about, so this edge state is 1 plus 1D in your system.
Right.
And so you have 3 circles And in the original material, it seems that these two circles are attached to each other, according to your picture. Spherical.
Right. So for example, so I have a so region A, boundary of region A is a circle. And then this part of the circle interact. So this part of the edge state of region A interact with the edge state of region C. But this part of the edge of region A interact with the edge of region B.
Can we think three CFT and just to paste with each other along this pasting curve?
Yes, yes.
And you can rewrite this in terms of this string.
Right. Right.
I see. Very interesting. But I have also another question about your previous part about what you said, Markov gap. I'm not so familiar with this quantity, but it seems the difference between reflected entropy and mutual information. And so what's the physical or some quantum information theoretical interpretation of this difference?
Right, I guess there's various, So I think there's various interpretations. So first of all, this is the interesting difference to take because R is bounded by mutual information. There's inequality, so it's natural to think about this difference. And then I think, so in this Markov gap, sorry, I didn't cite the paper which basically given this name Markov gap. That was from the Stanford group, Jonathan Soos and Onka Parika and Patrick Hayden. They relate this Markov gap to the some sort of I don't know actually exactly, but it's related to the recovery map of certain quantum recovery map. That's why it's called Markov gap. This group from Berkeley, they use this quantity to first they study this quantity first for 1+1D theories. And then they showed that this quantity is 0 for gapped ground state in 1+1D, which is written as some sort of unentangled state, which they call sum of triangular states. So they study, they basically show certain tensor network state. This is 0. But they also show that this is given by this number for 1+1D conformal field theory. I'm not sure if I'm giving anything very intuitive, but recently people started to accumulate some result for this quantity.
That's something. Yeah, thank you very much. That's very interesting. So it seems related to more entanglement, even though this reflected entropy and mutual information includes also classical correlation, but this seems to be more quantum.
So this seems to be more quantum, and then I think at least for the case of 1+1D, because of the result I mentioned, this is more like capturing some part of a multipartite entanglement.
I see. And your formula is universal for any CFTs?
So this formula is more like a lower bound, in fact. So in this field theory calculation, we just get this as it seems, but in the numerical calculation we get something slightly bigger. So what these people claim is that once you start from some topological phase, but then you can act with some local unitary to remove short-range correlations. Once you remove all short-range correlations, this is what you should get. But in general, there's some more contributions from short-range entanglement. So this is more like a lower bound for the Markov gap. That is consistent with our numerics.
I see. So it's related to interaction, how theory interact.
Yeah, it's like it's like yeah, it's related to short range interaction.
Thank you very much. So, is there any further questions? Okay, so we of course welcome question from younger generations. Question, but anyway, we have some coffee break time by using this virtual meeting tool called the spatial chat, which I just put in a chat here. So already, I think all of you got already email about this, but I just to make sure, I send this website, and you can just click this website, then you can go to, already Nagata-san gave a explanation of this, so you can just join this special chat, just click this site and go to this online coffee break time. Okay, so no question? Okay. Okay, so thank you very much for really wonderful talk, Shinsei.
Thank you very much.
Okay,
yes,
so
I'm sorry I went a little over time.
No, I think it's really good time.